Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Daniel Hafiz bin Sulaiman, DE210004. Okay, today our group will present our group project, which is about the fourth order bandpass active filter using op-amp. We are from the group 6, section 1. This is my group member. The first one is Engkami, AE210056. The second one, Muhammad Daniel Hafiz bin Sulaiman, DE210044, which is me. The last one is Nick Filzah binti Wan Baharudin, CE210150.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nick Filzah binti Wan Baharudin with the matrix number CE210150. So for this project, I will present the introduction. So a four-order bandpass filter, active filter utilizing operational amplifiers, is a circuit designed to selectively pass a specific range of frequency while attenuating others. This type of filter is commonly used in applications such as radio processing, communications, and instrumentation. The four-order design indicates that the filter comprises two cascaded second-order bandpass stages, each implemented with an op-amp circuit. Next is the discussion and importance of active filter in electronic system. Active filter are used in communication system for suppressing noise to isolate a communication of signal from various channels to improve the unique message signal from a modulated signal. The performance of electronic systems can be negatively impacted by noise and other undesired signals. In order to minimize this problem and guarantee that electronic system operates as intended, active filters are employed. The significance of active filters is in electronic system and their applicability to contemporary technology developments will to be discovered in this article. Next is type of filter. First is low pass filter, which is allow frequencies below a specific cut-off frequency to pass through the attenuator's highest frequency. Next is high pass filter, which is permits frequency above a specific cut-off frequency to pass through while attenuating lower frequencies. And last one is band pass filter, which is allow a specific range of frequencies to pass while attenuating frequencies outside the range. So this is one of the types of filter. So for the last one is importance of active filter in electronic system is first signal processing and frequency control, which is active filters are fundamental for signal processing, allowing designers to shape and control the frequency response of electronic system. Second one is noise elimination filtering, which is active filters are effective in eliminating unwanted noise and interference from signals. This is particularly important in applications where signal integrity is critical, such as communication system, medical devices, and also the instrumentation.
Okay, so this is the theory of bandpass filter. So bandpass filter is an electronic circuit that designed to ensure the signal within a certain frequency range to pass through and attenuating the signals that are out of range. So you can see here's a simple bandpass filter that is composed of two main elements, which is a low pass and a high pass filter. So this is a theory for the fourth order bandpass filter. So fourth order bandpass filter they will build up by using the operational amplifier. So this filter involves the cascading of two second order low pass filter and two second order high pass filter in series. So each of them will contribute to the overall selectivity and roll off of the circuit while sharing a common input and output. So this is a theory for bandpass frequency response. So the pass band for a low pass filter was begin from 0 Hz here and extend up to the chosen cutoff frequency point at -3 dB, which is below the maximum pass band range, the mid gain. So the pass band for a high pass filter will begin from -3 dB here, the cutoff frequency, and extend to the infinity or the maximum open loop gain for an active filter. So we have also referred to the Butterworth polynomial table. So for the fourth order bandpass filter, we will choose the fourth row to get the value of damping factor. So here's the manual calculation part. So for the fourth normalized denomination polynomial in factor form when n equals to 4, and the fourth row we will change, we choose from the table just now. We will get the value of both damping factor, which is df1 and df2. Their value will be 0.765 and 1.848. So to get the value of the gain of the both filter, low pass filter and high pass filter, we will use the formula here, and you sub the value of damping factor into the formula, you will get the gain value for both filter, which is 2.235 and 1.152. So for the low pass filter, we will assume all the resistance will be the same, which is 33 kilo ohm, and the RA1 and RA2 will have the same value, which is 10 kilo ohm. So to calculate the RF value for both filter, we will use the formula of a non-inverting amplifier, which is 1 plus RF divided by RA. So after we sub all the value into the formula, we get the RF1 value is 12.35 kilo ohm, and the RF2 will be 1.52 kilo ohm. So when we want to calculate the capacitance for in the circuit here, so we will use the cutoff frequency formula, which is 1 over 2 pi RC, and the given value of the low cutoff frequency, which is 1.5 kilohertz, we will sub it into the formula, and we will get the value of the capacitance, which is 3.21 nanofarad. Then for the high pass filter, we assume all the resistance have the same value, which is 3.3 kilo ohm, and the value of RA3 and RA4 is the same, which is 10 kilo ohm. Then we have do the same step as the low pass filter. We sub all the value into the formula, and we get the value of F3 is equals to 12.35 kilo ohm, and the RF4 will be 1.52 kilo ohm. Then we also use the given high cutoff frequency value and sub it into the cutoff frequency formula, and we get the formula of capacitance, which is 3.21 nanofarad, same as the low pass filter. So after we get all the gain value, we total it up by times all the gain here, and we get the value is 6.63. So it doesn't achieve the given mid gain value, which is 75. So we have to add an extra non-inverting amplifier. We assume it as A5. We cascading it at the end of the circuit. So how we get the value of A5? We will use this formula, which is the total gain is equals to the total of the full gain just now and times the A5. So we will, after you sub all the value into the formula, you will get the answers 11.31. Then the last thing we have to calculate for the circuit is the RA5 value. So we will use the formula of non-inverting amplifier, and we assume the value of RF5 is equals to 10k ohm. So after you doing by following all the steps here, you will get the RA5 value is 969 and 93 ohm. And the other things that we have to calculate in our project is the bandwidth. So for the bandwidth, we have to use the value of cutoff frequency to minus the low cutoff frequency. So the value that we get is 13.5k, and so on. The central of frequency, we have to square root the value of bandwidth. So we get the value of 4.743 kilohertz. And for the gain of band pass, we have to get if you want to calculate it in dB unit, so you have to put the unitless value into this formula, which is 20 log, and then sub the value gain here, you will get 37.50 37.50 dB. So the last is the quality factor. So how we get it? We will use the formula, which is Q equals to the central of frequency divided by the bandwidth. So you will get the value, which is 0.3513 here. Another thing is the circuit diagram and the component list. So this is our circuit diagram, which is built up by 2 second order low pass filter and 2 second order high pass filter. And here is the extra amplifier. It's the component list. We have the component that we have used in our project is the IC 741 operational amplifier, and resistor with 33 kilo ohm, and resistor 3.3 kilo ohm, resistor 10 kilo ohm, resistor 1.52 kilo ohm, resistor 12.35 kilo ohm, and resistor 1 kilo ohm. The simulation result, this is our simulation result. So you can see the value of the mid gain. You can, from the shape of the graph, you can see it is the same value here, horizontal line here. The value is 37.6. And if you want to get the value of low cutoff frequency and high cutoff frequency here, you can use the mid gain value, and then you minus 3, which is 34.6. So on the right side here, you will get the value of 14.5 kilohertz, which is the high cut-off frequency. And when you go to the left side, so this will be your low cut-off frequency, which is 1.57 kilohertz. For the analysis and discussion, here is our experimental simulation picture. So you can see our circuit here. Here's the op-amp and the resistor, the capacitor, and you can see there's a some jumper here. Okay, so next, this is the result for our mid gain. When we adjust our frequency to 7.60 kilohertz, we get the value of V peak to peak is 22.20 volt, and so same to the gain value in unitless, it is 22.20, and we convert the unitless value into dB, we get the value of 26.93 dB. So for the low cut-off frequency, when we adjust the frequency to 1.34 kilohertz, we get a value for V peak to peak is 19.20 volt, and same to the gain value in unitless, we get 19.20, and when we convert the gain value into dB, we get the value of 25.67 dB. And for the high cut-off frequency, when we adjust the frequency to 12.90 kilohertz, and we will get the value of V peak to peak is 19.20 volt, and the gain value in unitless will be 19.20. And when we convert the gain value into dB unit, we get the value of 25.67 dB. So here's a collection data for our experimental result, and the blue color one will be our low cut-off frequency and high cut-off frequency. So after we get all the value here, we plot a graph of frequency and gain value in dB unit. So you can see here is the shape of our graph. The mid gain here will be short. So we will explain why we will get this kind of result after this. So why we will get the sharp mid gain in our experimental result. The first reason is that the difference of tolerance of the passive elements such as resistor and capacitor. This situation will encourage the difference values of elements and inspire the difference output value. So you can see the cut-off frequency formula here. From this formula, the resistance in circuit and capacitance in circuit is inversely proportional to the frequency, and the tolerance is different. The value of resistor and capacitor will be changed, and the frequency will be changed also. We have also doing a comparison of simulation and experimental result. So you can see here is a big difference of the value of mid gain here between the simulation and experimental result. So here's the reason. The power supply value that we use is 12 voltage, 12 volt, which difference with the 15 volt power supply that used in simulation. So the difference of tolerance of the passive elements such as resistor is also a reason why the result will be like that. So from this formula, the resistance RF is directly proportional to the gain value, and the resistance of RA is inversely proportional to the gain value. So when there's a difference of tolerance value for the resistor in a circuit, then the voltage will be affected and change the gain value in the same time.
So for the conclusion for our project is bandpass filter are essential in wireless transmitter and receiver to limit the output signal bandwidth to the allocated band, preventing interference. They optimize the signal to noise ratio and sensitivity of a receiver, maximizing the number of signal transmitter in a system while minimizing interference. They are usually common in atmospheric science to filter recent meteorological data, ensuring only cyclone remain as fluctuation. It also used in various applications such as audio processing, signal conditioning, and biomedical signal processing, which is in ECG signal. Fault of the electrical bandpass filter can be simulated using a vented box with the driver cone resonate modified. It consists of 4 reactive components with a roll-off rate of negative 80 dB per decade. Its frequency response is characterized by a passband and a stopband, with the bandwidth being the difference between the upper and lower negative 3 dB point of the passband. The amplitude response is characterized by a peak at the center frequency of the passband with the Q factor affecting the bandwidth. Okay, that's all from our group presentation. Thank you.